Motor equivalence is a capability of the motor system to perform a particular task and produce the same movement outcome in a variety of ways. Even actions as apparently simple, repetitive, and consistent in outcome as writing as one's own signature on a piece of paper can be achieved through recruiting different motor units or even different muscle groups. So, motor equivalence is another highlighted portion here. Motor equivalence is a consequence of the many degrees of freedom, joints, muscles, motor units, we are able to independently control. Any plausible model of motor control must be able to account for how the nervous system rapidly and apparently effortlessly selects just one combination of joints, muscles, motor units from all the options available in order to perform a particular task effectively and efficiently. So, just to go back to that first sentence, motor equivalence is the capability of the motor system to perform a particular task and produce the same movement outcome in a variety of ways. So, okay, moving on to the next one. Serial order is the capability of the motor system to structure movement commands in such a way to reliably produce movement elements in a desired sequence. Okay. Corrective sequencing of movement components is fundamental to the process, to the performance of virtually all skilled actions, and errors and sequencing inevitably result in errors in performance. Serial order errors in speech give rise to spoonerisms. For example, movement instead of human movement, and in typing and transposition errors. CTA instead of CAT. So, and there you go. With the serial order, it's very complicated, the process of taking information and sequencing it in the right order. So we can see as people, our brains aren't perfect in doing this. Me personally, I do this quite often with the spoonerisms, switching the first letter of the first and last word in the sentence. It can happen. So yeah. In gross motor skills such as throwing, misordering of the recruitment of large proximal muscles such as those crossing the trunk, and smaller distal muscles such as those crossing the wrist joint, undermines the effective summation of forces and through this limits performance. A useful model of motor control must therefore be able to account for how serial order is generated in movement sequences and hence how errors may arise. So, we talked about in the paragraph, two examples of the serial order. It talked about, for example, how with our speech, structuring sentences and words, and how what can happen whenever these words are not lined up correct, right, or whenever the letters are mismatched. But also talking about physical movements, these things such as throwing, kicking, leaping may require multiple steps, a proper order, and not going through that order in a proper sequence can result in numerous things. Just a poor execution of the skill, or in some cases injury from falling, or other kind of injuries. Perceptual motor integration. It is the capability of motor system to produce movements closely matched to the current environmental demands perceived by the performer. Another highlighted text here, this is the bulk of the paragraph. Skilled movement is always subtly adjusted to meeting challenging environmental situations. For example, the skilled tennis player is able to adjust the racket swing if the ball deviates unexpectedly in flight. And all of us adjust our gait patterns if the surface we are on becomes irregular. So for example, with my last job, whenever I would come out the door, every time I was going on an order, there is a rock garden I have to cross. I don't have to cross, but I cross over it. Immediately when I get to that rock garden, the way I walk changes. So because the ground's very uneven, it's a very uneven surface with rocks that are shaped weird and are liable to move whenever I shift my feet, I would walk very slowly, very carefully, small steps, to adjust to those environmental demands. That way I did not fall or sprain my ankle. Okay. Such adjustment can be achieved only if there is a tight coupling and integration between perception and action. Such coupling must therefore be a key element of any satisfactory model of motor control. Okay, so back to the perception and action. I'm going to use the example I gave. So I perceive that this rock garden is not flat surface. It's not stable. It shifts under my feet. And then the second part is action. So once perceiving it and seeing that there are environmental demands, there is an action of changing my walking to a way I can cross this rock garden safely. Okay, because the role of particular muscles in either producing or opposing limb movement frequently varies according to contextual factors such as joint position or orientation of the limb with respect to gravity, the central nervous system, in issuing motor commands, must be continuously and accurately informed about the body's posture and position in space by its many perceptual systems. Right. And so you can see again how this is complicated, because there's a lot of moving parts. The nervous system has a lot of information to go through, sequence, and then come with an action. Okay. Skill acquisition is the capability of the motor system to learn and improve given appropriate conditions of practice. Explaining skill acquisition requires a motor control theory to, in turn, be able to explain how experience is stored and how, once acquired, movements can be modified to meet task conditions never previously encountered. A viable model or motor control must therefore be able to adequately account for the paradoxical capabilities of skilled performers to produce movements that are acceptable yet consistent. So, yeah. The capability of motor system to learn and improve given appropriate conditions of practice. So that's referring to how we learn skills and how we build on them. It's given appropriate conditions of practice. So an environment where you can learn the skill and where you can build upon it. Okay, next slide. Motor system as a computer. Computers are elaborate, engineer-designed devices used for processing information. Information processing models of movement control are based on the notion that the central nervous system, despite being biological in substance, is computer-like in function and that it is capable of sophisticated information processing. So here we go again. So this is how a model can be used to help us understand something such as the nervous system, because there's a comparison that states the way a computer operates with processing information and the way that our central nervous system operates with processing information is similar. Not the same, it's obviously not. We have biological matter on one, and when we have a computer made of chips and wires, plastic, metal, but that the processes are similar enough to make a comparison and to use a computer as a model, because a model is not a model, but a computer is something that we understand thoroughly since we have created it and we do improve them all the time. So, how then does the central nervous system act like a computer? Here we go. The input information for movement control is the sensory information sent to the central nervous system from primarily the visual, kinesthetic, and vestibular receptors. And so before we get to the example, I'm just going to say, like it says, how we take in information is through our senses, through our touch, through our visual, through our audible, mouth. That's how we take in information. Once we take that in, it goes straight to the brain, and from there it gets processed. A computer is a little bit different. While it can take visual and audio, it also can take in information through files, through an MP3, MP4. So it would be called. The output is the patterns of movement we observe and can describe biomechanically that arise as a consequence of the coordinated set of motor commands sent from the central nervous system to selected muscle groups. Input information is converted to output information through a number of information processing stages that take place in the brain and other regions of the central nervous system. The success of the movement that results the output depends primarily on the computational programs in the central nervous system that are responsible for selecting and then controlling the movement. Right. Programs like control, balancing, and GAT are there from birth and therefore may be considered part of the hardwire of the central nervous system. Other skills require programs and that are not innate and that must be developed, consistently modified, and improved through repeated use and practice. Okay, and here we have on slide 8, we have a picture here showing the comparisons of the brain and the computer. And so on the input for the computer, it has a keyboard for words for text entry, and a USB drive, which can include audio, MP3, MP4 information. And so that information goes to the computer, which is not the monitor. The monitor is just a display. The computer is the actual box with the hard drives, the chips, the motherboard, if you will. And the output of that can be, like I mentioned, the monitor, printer, speakers, and for the brain. So the example it shows is the visual system, the kinesthetic system, and the vestibular system. Goes to our brain. From our brain, we have movements. So it has the example of skilled movement. So someone taking in that a baseball is coming to them, process the information, how fast it's coming, location, where they are and relative to the ball, and the response is catching it. Or dancing. So interesting example could be listening to music. So the person takes in music they like. I like the way that sounds. Makes me feel good. Process the information, comes out in hopefully skilled movement of dancing. And so that's that for that one. Okay. Stages in a typical information processing model. Most information processing models of movement control assume that there are distinct and sequential stages through which information must pass, or more correctly, be processed from input to output. It is this information, environmental and internal information, that then provides the input for the central nervous system processes that ultimately produce as output motor commands, which are transmitted along the efferent pathways out the muscle fibers, where they individually cause muscle contraction and collectively generate observable movement patterns. Feedback for the movement itself is monitored via the afferent pathways and can be used to either correct errors in the movement if the movement is sufficiently slow, or make improvements to the commands for the next time the same or similar movement is to be produced. Okay. And so this is talking about, so we have now, we have the theory that our brain processes information in steps. So this is expounding on that. And we're going to get into the example here with the basketball player. So this basketball player here, he's perceiving that his opponent, this is a basketball example, that his opponent is about to make a jump shot. So he's perceiving that what's happening. This is his environmental and internal information is going in. Sensory reception. That information goes to his brain. Okay, I see him about to jump with the ball. Jump with the ball, he must be going for a jump shot. So with the information, I know he's going for a jump shot. He hasn't done it yet. What can I do? And this happens very fast. This happens in a matter of seconds, sometimes milliseconds. The output is that, okay, he's going for the shot, I'm going to jump and block it. So that is the perceiving, deciding, and acting stages of taking in the information. Visually, you can see what his player about to do, processes it for a moment, well, not even for a moment, for half a second. And within that short period of time, he's acting on what this other player is about to do. And that allows him to be able to block the ball. Okay. Stages in typical information processing model continue. Perceiving. The first important process that the brain and central nervous system must perform is that of perception. Perception involves selecting only the most relevant information for further processing and then using this information to determine what is currently happening and implicitly what is about to happen in the near future. In detecting stimuli, humans are limited by the range of physical stimuli to which the various sensory receptors can respond, as well as the capability to distinguish the firing of one or more sensory neurons from a background of general neural activity. Human ability to detect stimuli consequently varies from situation to situation, from one sensory system to another, in which factors such as arousal, humans are limited in their ability to compare and detect differences between two or more stimuli. Right? And so that's what perceiving is. We are taking in information, right? But the limitation of that is that we can only take in so much at a time or focus on so much at once. So focusing on one or two things, in many cases, is the limit for us as people. For a security system that has 3 cameras in one location or more, it is able to do that. But as far as human capabilities, we're very limited in that sense. And so we have selective attention. It is both it is both a limitation and advantage to human performance. We know from personal experience that our processing capability is limited and that we cannot listen to 2 separate conversations or attend to 2 separate visual signals, such as events in left or right extremes of our field of vision. Simultaneously, however, being able to selectively attend to only one thing at a time can be an advantage in that it provides a means of preventing irrelevant or potentially distracting stimuli from using some of our valuable processing capabilities. So yeah, we are limited in how much we can take in. The pros to that is that we are able to focus on the important information and tune out what isn't necessary in the moment. The problem is that we can only take in so much in situations where all of it is frankly needed.